Hello guys, welcome back to my YouTube channel Anveshana Academy. This is Dr. Manjunath Chennapgood. Dear students, in the previous class we discussed some numericals on conduction heat transfer using Fourier's law of conduction equation. And also in the last class I discussed some day-to-day activities which are related to conduction heat transfer. Dear students, come we will move towards next topic. So next topic is thermal resistance. So what is thermal resistance, dear students? So before going to thermal resistance, I will take two examples, general examples, and I will try to explain you what is resistance. So first we will try to understand resistance. Dear students, there is a stone, okay, spherical type of stone is there. It is falling down or it is moving down, but the man what actually is doing, with the help of his force, he is stopping the stone. That means what? He is opposing to the movement of the stone. That means what? He is resisting to the stone motion. So that means what? There is a resistance offered by man to the movement of the stone. That means what? Resistance we can call here the stone resistance which is offered by a man force. One example. So I will take one more example. What is the resistance? Dear students, assume that you are doing jogging or running in a track. Then what happens? Suddenly the high velocity wind will come. Then what happens? You can't run with high velocity. Why so? Because the air is going to act some force on you. That because of that force, what happens? There is a resistance to the movement of your body. So that we can call it as a resistance. That means what? Some force is going to exert on your body because of air. Hence what happens? There is a resistance to the movement of your body. That we can call it as a resistance. Okay. So now similarly, when it comes to heat flow, there is some resistance to the flow of heat. That we can call it as a thermal resistance, dear students. That what is that thermal resistance? Thermal resistance is nothing but what? Resistance offered to the flow of heat is nothing but what? Thermal resistance. Okay. How I can define technically? That you can see here, dear students. Okay. So now what is thermal resistance? Thermal resistance is a measure of a material's ability to resist the flow of heat. I repeat, thermal resistance is a measure of a material's ability to resist heat flow. That is known to be thermal resistance. That means what? You can take any material, dear students. What we are doing in heat transfer, we are transferring heat from one part to the another part of the substance, or one part of the metal to the another part of the metal, or non-metal, whatever you can take. For understanding, I will take a metal, right? So when you are transferring heat, right, that metal, what it will do? It will not transfer all heat immediately. So what happens now? It is going to resist to the flow of heat. That material, what actually it is going to do? It is going to resist to the flow of heat. That resistivity we can call it as a thermal resistance. That means what? Thermal means what? Heat. There is a resistance to the flow of heat. That we can call it as a thermal resistance, dear students. Okay, and that thermal resistance depends upon the temperature. What is the temperature? That I will explain in upcoming classes. Okay, fine. Now that thermal resistance, I can write it in terms of equation. That is, mathematically I can write like capital R is equal to delta T divided by Q. What is R actually? R is the thermal resistance, that is in Kelvin for watt, or degree Celsius per watt. So it is what? Here you can see it is degree Celsius or Kelvin, then heat is watt. So degree Celsius or Kelvin for watt, that is R, thermal resistance. Then delta T is what? Temperature difference across the material. Okay, that will be in terms of degree Celsius or in Kelvin. So as I told, dear students, the delta T is directly proportional to what? Resistance. Hence the change in temperature of the materials also play a very important role in the thermal resistance. Then where is Q? Then Q is equal to rate of heat flow through the material. The unit for heat transfer is watt actually. So this is what? Thermal resistance, dear students. Now I will try to take one example, engineering application, and I will try to explain you what is thermal resistance. And in technically in heat transfer we are going to call it as a thermal contact resistance. What is thermal contact resistance? That you can see here, dear students. Now generally we understood resistance is nothing but what? Resistance to the flow of heat is nothing but what? Thermal resistance. Okay, the formula for thermal resistance is R is equal to delta T by Q. Okay, this is what general. thermal resistance we can understood. But I will take one engineering application. That application is, there is a two materials, material A or solid A or solid B or solid material B we can call, dear students, and they are attached each other. They are attached each other. They are welded each other. You can see. Okay, now solid A and solid B are welded each other, are joined each other perfectly. Then at either side it is well insulated. That you can see at the top it is well insulated, and bottom also it is well insulated. That composite, we can say composite material. What is composite material? Combination of material A and material B. We are going to get one material. That material I will call here as a composite material, dear students, for this application. Okay, so for that composite material definition in detail we can study it in composite material subject is there, material science is there. There we can study in detail. But generally what I am doing now, to understand heat transfer, I am taking material A and material B. I combined here these two. I am calling here as a composite material. But actual definition of composite material is different. That I will not discuss here. Okay, now this is composite material. I can say it's a combination of material A and material B. I am going to transfer heat at this end. From this point to this point, what I am doing here, I am passing heat. Hence heat is transferring in only one direction. That is very important, dear students. Heat is not transferring in either direction. Why so? Either direction it is insulated perfectly. Hence there is no heat transfer. The heat transfer is going to take place from point 1 to point 2, or you can say in horizontal direction, or that too in a x direction. We can say, dear students. The high temperature region I will mark here as a T. I will mark temperature as T1, whereas low temperature region I will mark temperature as a T2. Then what actually happening now, dear students? The heat is flowing in this direction, right? There is a decrease in the temperature. Yes, decrease in the temperature in material 1, that is having same thermal conductivity, that is K. Okay, so because of same thermal conductivity, because in homogeneous material A, so heat is going to transfer gradually. That means what? Temperature decrease will be linear and gradually. Once it reaches this particular point, right, it's a small gap, very very small gap, that we can see it in microscopic level. But when we're seeing it outside, it looks like a contacted completely and joined perfectly. No, but when it comes to practically, with help of microscope, we can see there is small gap between material A and material B. That gap we can see here, dear students, now. Okay, so now, so what will happen? If there is a small gap that we can see here now, this is what small gap. Here it is a material A and material B. When the heat is transferring in this direction, right, then heat is going to drop in the small gap. So that drop we can call it as a temperature drop due to thermal contact resistance. Okay, then heat will transfer. Okay, that you can see here now. Then heat is going to transfer again from here to here, from this point to this point, again same thermal conductivity of material 2. Because of that, what happens? Linear temperature gradient we are going to get. That means what? Linear temperature decrement we can see here now. That I can show it in a linear line actually. So because of the thermal contact here now, because of this contact of these two body, there is a drop in the heat flow. That means what? There is a resistance in the flow of heat, that we can call as a thermal contact resistance. Okay, that I can show it in the temperature versus distance graph here now. That you can see here now, dear students. Y axis I will take a temperature, then x axis I will take it as a length of the composite wall or thickness of the composite wall we can call. So initially from this point to this point, okay, so initially it is having high temperature region. I will mark here high temperature region. In material 1, temperature is decreasing linearly, so I mark here now from this point to this point. When reaches the gap, right, when the heat reaches the gap, right, then what happens? Temperature is going to drop. That drop in temperature here, the temperature is going to drop means what? It is going to decrease. So when it reaches this point, right, that I can call it as a TC1, temperature at thermal contact 1, then TC2, thermal contact temperature at thermal contact 2. That means what? TC1 and TC2 are the temperatures at thermal contact or resistance offered due to void. This we can call it a gap between solids, or we can call it a air voids also, dear students, air voids. Okay, because of the air voids, temperature is going to drop. That too from TC1 to TC2. That drop in temperature I will mark here as a delta T. Okay, then okay, fine. Next, then what happens? Now the temperature is going to decrease. the temperature is going to decrease from this point to this point linearly. That means what? Tc to T2, again linearly. There is no drop in because it is having same thermal conductivity. Here also same thermal conductivity, here also same thermal conductivity. Hence decrease in temperature is linear along the thickness of the material. But here also same, because of same thermal conductivity of material A, linear temperature decrement in the material A because of same thermal conductivity. But when it reaches right here heat, there is a sudden drop in temperature or resistance to the flow of heat. That resistance, the drop in temperature, I will mark here as a delta T, where delta T is equal to temperature contact at resistance 1 is equal to temperature at contact resistance 2. That is nothing but Tc1 minus Tc2. So this is about thermal resistance, dear students. Now how it is that we can see now, dear students, in detail I will take a schematic diagram and I will try to explain you what is thermal contact resistance. Dear students, I have taken two metal plates, I have joined each other, then I am transferring heat from one end to another end. Because of that small gap in the contact between two materials, there is a drop in temperature, or we can say there is a resistance to the flow of heat. How it is that we can see here, dear students. This is material A and it is a material B. The heat is transferring in this direction. Heat is transferring in this direction, that I will mark here as a Q. Okay, fine. So if there is a small gap, if there is a, assume that in this particular portion, I will take a whole metal body, metal body A and metal body B. I have taken thickness, you can take 1 meter or whatever it may be. In that very small, in terms of microns, you can take, if the material A and material B are contacted perfectly, small micro length, if it is contacted completely, if the heat is transferring in that fashion, that we can call it as solid conduction heat transfer. But you can take in another side, you can see here this side, if there is a small gap between material A and material B, due to that gap there is a drop in temperature and there is a resistance to the flow of heat, that we can call it as a interterrestrial heat transfer. Because of the air void or air gap, the heat is going to there is a resistance offered to the flow of heat, that we can call it as an interterrestrial heat transfer. Again, at this particular point, dear students, you can take material A and materials B are small micro length, they are contacted each other. If it's so, again solid conduction. If there is a gap between material A and material B, that if the heat transfer is taking in that particular condition or case, we can call it the interterrestrial heat transfer, dear students. Okay, here we can say solid conduction again. So if it's so, then what happens now? I can show that variation in temperature or temperature drop, I can show in a temperature along the thickness of the plate. How it is that you can see? Y-axis I will take temperature, dear students. Here is the high temperature because material A having same thermal conductivity, whatever the heat is going to transfer in that, right? It is a linear, it is a heat transfer, there is no any resistance. Okay, then once the heat enters the air gap, right, or air void, then what happens? There is a drop in the temperature. Once the heat is transferring that material, there is a linear temperature gradient. That means what? Decrement temperature is linear. T1 to T2 we can say. Okay, T1 to I can call it as a TC1. Okay, temperature contact resistance TC1. I will call it here as TC2. But here I will mark it as a T1 and here I will mark it as a T2. Okay, fine. Heat is transferring from material, this is material 1, I will mark here as a Ka. Then resistance, thermal conductivity at here is Kb. But when it reaches, right, heat, this is the air gap, right, there is a drop in temperature. That is nothing but what? There is a drop in temperature, that I can call it as a delta C. Just a minute. Here I can call here as a delta T. Where is delta T? Delta T is nothing but what? Tc1 minus T2. That is a drop in temperature due to cause of air gap. Okay, that I can see. Again, once the heat reaches the second materials, right, in that second materials, what happens? Heat is going to transfer normally, then temperature gradient is linear. So that I can show it here now. From here to here it is a linear line because of the same thermal conductivity in material 2. That is nothing but what? That is how the temperature is going to drop. Hence, because of this temperature drop, what happens? The heat transfer is, there is a resistance to the flow of heat flow. That we can call as a thermal resistance, dear students, or we can call thermal contact resistance. To understand better, we can take one more example here, dear students. What are those? So you can take a material A and material B I have taken. I have contacted each other. The temperature at this point, height, I will call it as a high temperature region, and this I will call it as a low temperature region or phase B. Heat is, whatever the heat is there, right, at this point I will mark here as a T1. Here I will mark as a T2. 1 minute. So heat at this point, right, I will mark here temperature. So temperature at this point I will mark here as a T2, T1. Temperature at this point I will mark here as a T2, dear students. Okay, fine. The heat is moving in this direction from phase 1 to phase 2 or phase A to phase B. When the heat is going to transfer in material A, right, you can call it as a material A, dear students. You can call it, okay, it is not visible. I will write it here. It is a material A and it is having material B. Material A having thermal conductivity, that I will mark here Ka. Then material B having thermal conductivity, that I will write it here Kb. The heat is going to transfer in material A, right? It's the same because of the same thermal conductivity in material A. There will be temperature drop will be linear up to this point. Then once he reaches this point, right, junction, or we can call it as a connection point, what will happen now? There is a small air gap that we can see it in micro level. That because of that small air gap, what happens? The temperature is going to drop. The temperature I can mark here as a temperature drop. Then that I need to draw it like this. Okay, so that small drop in temperature is there because of the air gap. Hence what happens? There is a resistance to the flow of heat. That resistance we can call it as a thermal resistance, dear students. Okay, once it reaches material 2, right, then what happens? The material B having same thermal conductivity. Hence what happens? There is a linear drop in the temperature. That is TC2, you can call it as a TC1, you can call it as a TC2, TC2, T2. There is a linear temperature that I can show it to you now. How it is, dear students, that one thing you can see here now. What I have done, there is a small air gap. The air gap, when it is contacted, right, this I can show it here now. So this is material A, I can call, 1 minute. Okay, so I will call it as a material A. This I will call it as a material B. It is material A and it is material B. They have contacted each other, but there is a small gap between the two materials that we can see it in microscope. Because of that small gap, that we can call it as a air gap or air void. Because of that air void, what happens while transferring the temperature, right, the temperature is going to drop and it will move like this. So it is T1 and it is TC1, okay, and it is TC2 and it is going to T2. So that means what? Temperature is going to drop at this particular point. 1 minute. Okay, so now temperature is decreasing. The same thing I will show it in the temperature diagram. How it is that we can see now. Dear students, we can see now when it is at material this point.